Okay, so a little bit of background here. What I've made is a sound card that works with the HB6809, my homebrew computer. And it's based off of essentially the Disney sound source, which is a Covox uh, like parallel port 8-bit DAC. Um, it uses a resistor ladder um, and a small op amp to amplify its output in a box with a speaker. And it has what's called an amplifier board, which isn't the amp, um, but it's a little dongle that plugs into the parallel port um, that has a 16-word flexible register, um, which is a FIFO, and a 555 timer, which sets the sample rate between 6.5 and 7.8 kilohertz. So how you program it is you send code or set up code that sets the parallel port output for each sample of the DAC, and then it strobes that data into this register and checks each time it does a strobe to see if the register is full. It doesn't have the ability to determine if the register has emptied, like in a situation where you have a data underrun inside your register. It just checks to see if it's full. And to accomplish that, it uses a CPU software interrupt with the timer chip inside the PC. And the benefit to this over the Covox is that you get a longer interrupt duration because the sample clock inside the dongle and the 16-word flexible register, it handles a lot of the heavy lifting for you. The disadvantage is that this 6.5 kilohertz sample rate is abysmally slow based off of even just a regular 8088 doing 100% of the timing, like in a Covox setup where it's just literally a resistor DAC sitting on the parallel port, and the computer is handling a software interrupt at exactly the same rate as the sample clock. So in that case, you could have a lot higher quality and still achieve side tasks even with the like say even twice as much, like 22 kilohertz. So in that case, this was kind of critically ridiculed for its low sample rate, and that's one of the things that I address in my design. Let's take a moment to thank our sponsor, PCBWay. PCBWay has again kindly offered to sponsor the prototyping phase of the HBSound project. If you don't know, PCBWay is a one-stop shop for PCB rapid prototyping, sheet metal fabrication, as well as many 3D printing options. If you're considering having anything made, PCBWay offers fast, affordable options for most of your prototyping and fabrication needs. Thank you again, PCBWay. Okay, so HBSound is different from the Disney sound source in that I'm using a discrete DAC, the TLC 7528CN, with one of its available 2 channels, which feeds into a transistorized preamp for managing noise and setting the output levels up for a external amplifier. I use the same type of flexible register of FIFO 16 words, and in this case I have fully latched the 2-bit flags in the correct timing interval to make them useful to the programmer. That is clocked out by an 8-bit counter controlled state machine, which is just an EEPROM with the appropriate clock rate pre-calculated using a 2-bit control word. So that would be 32 kilohertz, 16 kilohertz, 8 kilohertz, and 7.2 kilohertz. And that's set by the 2 bottom bits of the control word. And then you can stop or start the clock using the 3rd bit. So that's considerably better than the Disney sound source because you have all those other available clock rates. Still controlled by code, set by the programmer, sending the samples to the FIFO. You still have that same long duration that is defined by a software interrupt. But in this case, it's very easy to improve on the design because the flags are now latched at the appropriate time so that they could be used for a much more sophisticated hardware interrupt setup if in a future design I wanted to use them that way. But in this case, it's just available to the programmer by reading the address space for the mapped device. Additionally, this whole device is available on the bus as a addressed device. Okay, so this is the simulation made in Neeman's Digital, which is a logism clone that was written from the ground up and has a lot of real nice features for state machines. You want to take a look at what makes Neeman's Digital different, you can go and take a look at his GitHub repository. I can link it in the description of the video. Essentially, the control logic is 3 parts. There are discrete logic for creating signals down here, a state machine, and a control register with flags register. So the discrete logic is just 7414, which is a Schmidt trigger inverter, hex inverter, and a 7400, which is a quad NAND gate. Essentially, what it does is generates the reset signals for the registers, generates a not read signal for the flags register, manages ANDing together the flags from the 4-bit FIFOs so that the 2 signals from each FIFO, or the same signals from each FIFO, generate a single output, not inverted output, which, as long as you know it's inverted, makes no difference to the programmer. So those signals are sent to the latch to be latched at the appropriate time. And then we OR the state machine output with the system clock so that when the output of the state machine happens, when it generates its interrupt, which will be just here in a second, as you can see, this shift out is the output of the state machine. Or the shift out is actually the output of the OR gate. The RC is the output of the state machine. So this is low for one full cycle. And we only need the shift out signal to be low when the system clock is low. And that's important because once this goes high, we can use a high signal to immediately latch the value of the registers inside, or the flags inside the FIFO register. If we latch them when it's low, or we try to read them when it's low, or we try to use them for an interrupt when this is low, the state of those flags is actually busy. You can read about that in the datasheet for the FIFO, which I'll also link. But essentially, you only want to latch the flags from the FIFOs when it's high. So we have to OR the output of the counter reset with the system clock, so that when they are both low, we only send a low signal to clock out the data on the FIFO. So that's how that works. And we make an OR by simply just inverting the inputs of a NAND gate, which you can build in logism if you want to see how that works. And then we also make a write signal, similar to the way the HB 6809 makes its not write signal, but we invert it, so that when we can clock the input of the FIFO on a high signal when the clock is high, essentially. So when the clock goes high and the write signal is high, the write signal goes out to the latches, or the registers inside the device. That's how this logic works. And then we have the two counters, a high and a low 8-bit counter, and they feed into an EEPROM, which is not actually a 28 Charlie 256 in the design, but this is what's available in Neeman's digital, so that's what I used. The state machine state is controlled by address lines 8 and 9. That's set by this register, which can be written when the address line is high. So if you send a value to the interface address +1, that will set the control register. If you send a value to the interface address, it will send a value to the FIFO. And the triggering for that is handled by the flags buffer, which also manages whether or not we put the flags onto the bus in a read. The buffer also actually takes this third bit, which is the clock enable line, and when it is low, the clock is allowed to go through to the FIFO, and when it's high, the clock is inhibited. And that is actually a change in the 4th iteration of the design that was required because I had to... there was an issue with the datasheet, and it's not very clear as to how this output enable on the FIFO actually works, which I'll probably go into when I do a full write-up on the interface on Hackaday, but just for the purposes of the explanation of how the logic works, the clock needed to be arbitered instead of the output enable bit on the FIFO, which does not work the way that it doesn't work the way that you would expect it to work, basically. So that's essentially the logic. Okay, so then we have these two bus transceivers that basically are HCT bus transceivers, and essentially they handle all of the bus access, and the only signals that come straight through are the system clock. We also have a buffered version of it, and the reset line, which basically we want to be able to reset the registers whether or not the bus is enabled from these transceivers. So that was mainly the reason for using these, was basically to get tri-state all of this so that it's not just hanging off the bus, because it gets a little busy with all the expansions ports on the interface, and the serial adapter currently has no transceiver at all, so I didn't want to overload the bus, and that's why I use these. So that's basically it. I did some simulation on breadboards for individual parts, but this actual EEPROM was actually able to build as a discrete logic component and then output a truth table, which I was able to import into my tool chain for creating EEPROMs, and that worked really, really great, which I really like Neeman's digital better than regular logism. I highly recommend it, and again, like I said, I'll link it in the description. So that's how all of this works. So that's about it. I appreciate all the kind feedback on these projects, and as always, I'll put more details up on the project site for those who are interested. If you want to, subscribe if it interests you, and as always, thanks for watching.